Good morning. This morning we're going to continue with limiting reactants from yesterday's assignment. So let me take you to the laboratory of chemistry matters at GPB.
Welcome back to Chemistry Matters Unit 6, Moles and Stoichiometry. There are many factors that affect the amount of product formed in a chemical reaction that we haven't yet discussed. For example, what if you had a factory that was producing a semiconductor material for use in computers, and you found that changing the amount of reactants, the recipe you were using, also changed the amount of product you were able to make? You'd probably be very interested in determining how to maximize the products you make, and you'd probably also want to maximize your profit. For example, in this problem from the last video in the Unit 6 playlist, we calculated mass of silver, but we didn't mention the other reactant, the silver nitrate, other than saying it was in excess, that was involved in the reaction. Since atoms and molecules must collide in order to react, the amounts of the reactants that we have before a reaction will dictate how much product can be produced. Typically, one of the reactants is completely consumed in a chemical reaction, and once this happens, the reaction comes to an end. Let's head back to our classroom, where our students are getting a chance to see how the amounts of reactants in a chemical reaction can affect the amount of product that can be made.
In this activity, we're going to use the creation of s'mores to explore how the relative amounts of reactants used in a chemical reaction will determine how much product can be formed. So pretend we're starting a company that makes s'mores and sells them for a profit. The ingredients we'll use will be like reactants in a chemical reaction, and the finished product, the s'more, well, it'll be like a product that's made in a chemical reaction. So take a look at the activity sheet I gave you. Each group has also been given a specific amount of graham crackers, marshmallows, and chocolate pieces. Right? So answer the questions as your group proceeds through the activity. And remember, even though the lab materials look delicious, for safety reasons, there's no eating in the lab.
Okay, so the first question asks, what do you need to make a s'more? So we need 2 graham crackers, a piece of chocolate, and 1 marshmallow. And the second question asks us to write out a reaction for how to make 1 s'more. All right, we can abbreviate these. So let's write 2GC for graham cracker, and plus 1CH for chocolate, plus 1M for marshmallow equals 1 s'more. So now we need to see how many we have of each. So we have 14 graham crackers, 4 pieces of chocolate, and 9 marshmallows. Okay, let's put these together and see how many s'mores we can make.
Okay, Team 1, looks like you finished making your s'mores. How many were you able to make?
We were able to make 4. We could have made more, but we ran out of chocolate. We still had 6 graham crackers and 5 marshmallows left.
Very good. Team 2, how many s'mores were you able to create?
Well, we started out with 8 graham crackers, 5 pieces of chocolate, and almost an entire bag of marshmallows.
So we were able to make 4 s'mores.
Yeah, but we ran out of graham crackers. We had 1 piece of chocolate left over and a lot of marshmallows.
Great job, everyone. What you all just demonstrated was the concept of a limiting reactant. A limiting reactant is the reactant in a chemical reaction that limits the amount of product formed. The reaction stops once the limiting reactant is consumed.
Right, I hope you're taking down your notes.
So if we take a look at the equation for the creation of our s'mores, we can see the proportional relationships between the amounts of reactants and the product in our reaction. So for group 1, you guys ran out of chocolate because you had only 4 pieces. So when you ran out of chocolate, you couldn't make any more s'mores, your product. So if this were a true chemical reaction, we'd say the chocolate was the limiting reactant, because once it was completely consumed, the reaction stopped. Therefore, the chocolate limited the amount of product that could be made. The leftover graham crackers and marshmallows that you had after the reaction are analogous to excess reactants, if this were a reaction. The excess reactant is the reactant in a chemical reaction that remains when a reaction stops once the limiting reactant is completely consumed. The excess reactant remains because there is nothing with which it can react. Group 2, what would you say the limiting reactant was for your experiment?
Well, we ran out of graham crackers, so I would say that was our limiting reactant. Once they were all gone, we weren't able to make any more.
Yeah, and our chocolate and marshmallows were our excess reactants.
Exactly. So chemists sometimes have to determine which reactant is the limiting one in a reaction in order to determine the amount of product that can be formed. This amount of product that can be formed is known as the theoretical yield. Theoretical yield is the amount of product formed from the complete conversion of a limiting reactant in a chemical reaction. When it's unclear to chemists which reactant will run out first, a calculation to determine the limiting reactant and therefore the theoretical yield is required. There are many reactions, however, in which it is very clear which reactant is the limiting one and which reactants are in excess. If we know this information to begin with, then we can calculate theoretical yields based on the amount of the reactant that we are given to begin with in the problem. So let's look at an example together. Ammonia can react with oxygen to produce nitric oxide and water. So let's say that you operate a factory manufacturing nitric oxide for heart medication. Your starting materials are ammonia and oxygen. In your factory, let's assume that it's very important to know exactly how much water will be produced by this reaction, since you're careful to recycle as much water as you can. So given this balanced chemical equation, where 4NH3 plus 5O2 yields 4NO plus 6H2O, when 1.2 moles of ammonia reacts, how many moles of water should be produced? Now, here's a perfect example of a problem in which we know which reactant is going to be limiting from the start. Since the atmosphere contains about 21% oxygen gas, there is more than enough oxygen present for this reaction to go to completion while completely consuming the 1.2 moles of ammonia. So let's do a stoichiometric conversion to solve this problem. Now, the first step would be what, Michelle?
Place what is given to you in the upper left-hand corner of a conversion chart, which would be 1.20 moles of NH3.
Good. And what's next?
We let the units guide the conversion, so we bring down the moles of NH3 down to the next denominator of our chart.
Great. Then what do we do?
Since we have the moles of what was given, we can do the mole ratio step.
So we use the coefficients from the balanced equation to convert from moles of NH3 to moles of water. We put a 4 in the denominator in front of moles of ammonia, then put 6 moles of water in the numerator.
Yeah, so that allows us to cancel the units of moles of NH3, and we'll be left with moles of water, which is what we want. So let's just multiply 1.2 times 6, and then divide that by 4, and our answer is 1.8.
So 1.8 moles of water is the theoretical yield, and that amount of water can be made from 1.20 moles of ammonia according to that reaction.
Well done, everyone. That was nice work by our students as they tackled many concepts, such as limiting reactants, excess reactants, and even theoretical yields. This unit also has a closer look video on limiting and excess reactant calculations, as well as several other closer look videos.
Another thing our teacher mentioned at the end of the last segment was how the theoretical yield measured the amount of product that could form from the complete conversion of a limiting reactant to products in a chemical reaction. Well, what happens when a chemist performs a reaction and the amount of product that he or she actually recovers is different than what the calculated theoretical yield was? This actually occurs more frequently than you might expect. And chemists are always trying to evaluate their lab technique so that they can run experiments that are more accurate and precise. To that end, one of the most effective ways that a chemist can analyze their recovery data is with a calculation known as percent yield. Percent yield is the ratio of the actual yield and the theoretical yield of a material.
Percent yield is a measure of the reaction's efficiency.
It's determined by comparing the amount of product that's actually recovered in a lab when the experiment is run, known as the actual yield, to the theoretical yield, which is calculated using stoichiometry. The formula for percent yield is actual yield divided by theoretical yield times 100, which converts it to a percentage. It can be the first indicator of a source of error in the experimental design. Percent yield is always calculated after an experiment is complete because the actual yield from the experiment is required in the calculation. It'll help to walk through an example of a problem in which a percent yield is calculated. Potassium chloride is used to make fertilizer for plants, and it also has medical uses in treating patients with low potassium levels. Let's say you work in a lab manufacturing potassium chloride. When 45.8 grams of potassium carbonate reacts with excess hydrochloric acid, 46.3 grams of potassium chloride are formed. Calculate the theoretical and percent yields of potassium chloride. The first thing we need to do is calculate the theoretical yield of potassium chloride, since we'll need that number to plug into the equation to solve for percent yield. Since the hydrochloric acid is in excess, we can base our calculation off of the other reactant, potassium carbonate, since we know that it's the limiting reactant. So setting up a stoichiometric conversion chart, place 45.8 grams of potassium carbonate in the upper left-hand corner, and then bring down the units to the denominator of the next column. Then use the molar mass of potassium carbonate, which is 138.21 grams, to convert to moles of potassium carbonate.
All right, this is calculating the molar mass of potassium. We have 2 potassium. We multiply potassium atomic mass by 2 plus 1 carbon plus 3 oxygen. The total will give us 138.21. And remember the grams, we cancel the grams. This is the conversion factor that you're supposed to know by now. Whatever unit you have here must always be at the bottom so that they can easily cancel out. And when you're looking for atomic or molar mass, you always have 1 mole of that substance at the top.
Now, since we've converted to moles of potassium carbonate,
we can use the mole ratios from the balanced equation to convert to moles of the desired substance,
in this case, potassium chloride. Next, since we need to solve for the theoretical yield of potassium chloride, we would convert from moles of potassium chloride to grams of potassium chloride by bringing down our unit of moles of potassium chloride. Then we can use the molar mass of potassium chloride, 74.55 grams, to convert to grams in this last step. Notice that we're canceling our units, grams of potassium carbonate and moles of potassium carbonate, along the way. We can now multiply 45.8 times 1 times 2 times 74.55, and then divide that by the product of 138.21 times 1 times 1, and we find the theoretical yield of potassium chloride is 49.4 grams. When we use 45.8 grams of potassium carbonate. Now that we have the theoretical yield, as well as the actual yield that was given to us in the problem, we can solve for percent yield by simply taking the actual yield, 46.3 grams, and dividing that by the theoretical yield, 49.4 grams, and then multiplying that by 100. We find that the percent yield in this particular problem is 93.7%. The factory was able to produce a very high yield of potassium chloride, almost 100% of the predicted amount.